U-Matic.
We ourselves cannot venture into deep space, but we have sent explorers, mechanical explorers, to distant planets and on to the limits of our solar system to be our eyes and our ears for us. These spacecraft, however, are only as good as our ability to communicate with them, to track them, guide them, and above all, to receive the data they send back. Information that could not be learned from Earth. This presentation is about the organization that listens to our spacecraft and communicates with them, the Deep Space Network. We send our spacecraft on ever more complex assignments and to ever more remote regions of the solar system. To accommodate this increasing sophistication of our space program, the Deep Space Network, often called the DSN, has grown over the years into an international complex of tracking antennas as well as data handling and communication systems. As we shall see, the DSN has evolved incredible abilities to track spacecraft, measure their velocities, correct their courses, and to receive their data. The origins of the present Deep Space Network trace back to the early 1950s in Caltech's Jet Propulsion Laboratory at Pasadena. At that time, the Army needed an accurate and reliable guidance system for its Corporal ballistic missiles, and the California Institute of Technology was under contract to develop it. By adapting the principle of the phase lock loop, scientists at Caltech's Jet Propulsion Laboratory created a successful missile guidance system. But they also perceived that phase lock loop technology might be useful in tracking future spacecraft by detecting weak spacecraft signals immersed in a background of random noise, and by measuring shifts in frequency due to Doppler effect. The opportunity to test this theory came in 1958 with the Army's Explorer satellite, the United States' first successful orbital spacecraft. A JPL-designed system called Microlock successfully tracked Explorer, and the phase lock loop was established as the basis for all future spacecraft communications technology. 1958 also brought JPL another tracking assignment. The Army had a newly funded program called Pioneer, lunar probes that for the first time would send U.S. craft into deep space. The Pioneer probes would be tracked by an expanded space tracking network. One station at the Cape to track the launch phase. A second station in the vicinity of Puerto Rico for the near-Earth phase. And a third station, a deep space station, to track each probe's lunar trajectory. The site selected for the deep space station was on the Army's Fort Irwin Military Reservation in California's Mojave Desert. 50 miles from Barstow and about 100 air miles from JPL, the new station would be located in a natural bowl-shaped basin surrounded by hills. The hills would help shield the antenna from the man-made radio noise, an essential feature for receiving very weak signals from deep space. Not far away was Goldstone Dry Lake and a nearly deserted old mining town called Goldstone, whose name was given to the deep space complex that would develop there over the years. Tracking Pioneer required a very narrow beam antenna in order to provide sufficient gain for the received signal. A 26-meter diameter parabolic radio astronomy type antenna was chosen. JPL engineers modified it for desert conditions and increased its efficiency by use of improved lower noise receiver technology. The antenna site was christened Pioneer in honor of the mission. Today, this first deep space station is also known as DSS-11. The new 3-station space tracking network, including the installation at Goldstone, successfully tracked Pioneer probes 3 and 4. At that time, the tracking network was under the control of the Advanced Research Projects Agency. In 1958, overall responsibility for these tracking facilities passed from the Advanced Research Projects Agency to its successor, the newly created National Aeronautics and Space Administration, NASA. One of NASA's first undertakings was Project Echo, testing balloon-type satellites as passive communications devices. According to the project plan, an L-band signal would be transmitted from the Bell Laboratories facility in Holmdel, New Jersey, bounced off an Echo satellite, and received by Goldstone's 26-meter Pioneer dish. A new antenna built at Goldstone would return an S-band signal. S-band because scientists were interested in testing this higher frequency for possible future use in deep space communications. This new antenna, appropriately named Echo, became operational in 1960. Its high-speed azimuth elevation type drive was more suitable for tracking satellites than the equatorial drive on the Pioneer dish. Goldstone now had 2 deep space stations, DSS-11 with its Pioneer antenna, and DSS-12, the Echo antenna. Project Echo accomplished many significant experiments in long-distance communications, including the first coast-to-coast satellite voice transmission. New improvements in receiver noise temperatures were also accomplished through the use of parametric amplifiers on the Goldstone antennas and liquid helium-cooled masers at the Bell facility in Holmdel. Goldstone was also called on for other non-tracking assignments. Radar moon bounce experiments with the 26-meter Echo antenna confirmed the value of the deep space stations as astronomical tools. And on March 10, 1961, while the Echo antenna transmitted, the Pioneer dish received the first indisputable radar echoes from Venus, a two-way contact at a record 75 million miles from Earth. Echo transmitted a 13-kilowatt continuous wave signal, and Pioneer listened with new sensitivity provided by a liquid helium-cooled maser driving its parametric amplifier. The Echo antenna was moved in 1962 to DSS-13, also at Goldstone, and renamed Venus. It is now used for research and development in spacecraft communications. DSS-12 subsequently received a new 26-meter equatorial drive antenna, which assumed the name Echo. By now, the space race was in full swing, and NASA objectives called for tracking and communication with deep space probes on a 24-hour, uninterrupted basis. This required a network of 3 deep space stations positioned about 120 degrees of longitude apart. In 1960, a 26-meter antenna was erected 14 miles southeast of Woomera in the Australian desert. In 1961, a 26-meter dish was installed 40 miles north of Johannesburg, South Africa. These 2 facilities, together with Goldstone, comprised a network of 26-meter antennas that came to be known as the Deep Space Instrumentation Facility, the DSIF. Linked to JPL's communications center in Pasadena by 2 teletype circuits and 1 voice circuit per station, the new DSIF was ready for its first assignment, tracking the Ranger lunar probes. During Ranger and succeeding missions, the Deep Space Network, or the DSIF as it was then known, continued to make important discoveries in low-noise receiver design and space navigation. A monumental contribution was the Double Precision Orbit Determination Program developed by JPL mathematicians and programmers who synthesized the mathematics of celestial mechanics into a single computer program. Using this important tool, mission operations personnel could now generate spacecraft maneuver commands which would take into account celestial gravitation effects and celestial motion, as well as position and velocity of the spacecraft. With missions increasing in number and complexity, the Deep Space Network soon faced the task of supporting several spacecraft simultaneously. This, together with requirements for higher data rates and real-time mission decision-making, prompted the creation of a separate space flight operations facility at JPL in the late 1960s. High-speed data lines now fed spacecraft data directly to computers for processing. The data was carried to JPL via intersite microwave communications links and NASCOM system satellites. However, teletype circuits and voice comm circuits were still maintained. By now, NASA's plans called for very long-range deep space probes, missions to the planets and beyond. The Deep Space Network of the 70s was formed with the construction of giant antennas capable of tracking and communicating with probes to the edge of the solar system. 64-meter diameter parabolic dishes were erected at Goldstone in Australia and Spain. Meanwhile, the old Johannesburg and Woomera sites were deactivated. The old teletype circuits were also deactivated, replaced with wideband as well as high-speed data lines for the Viking Mars missions and the Voyager deep space probes. A major overhaul and upgrade of DSN data systems was implemented. Today, a new generation of mini-computers and supporting peripherals known as the Mark III data system is the result of the Deep Space Network's ongoing efforts to keep current with the state-of-the-art telecommunications and data handling. Today, the Deep Space Network maintains installations in Australia, Spain, and the United States. In the Tidbinbilla Valley of southeastern Australia, near Canberra, are Deep Space Stations 42 and 43. The 26-meter dish at DSS 42 is called Wimala, an Australian Aborigine name meaning a distant view. Station 43's 64-meter dish is Balima, meaning very far away. Wimala and Balima are called conjoint stations because they share the same location and have several facilities in common. A few miles away at Honeysuckle Creek stands the 26-meter dish of DSS 44, the only antenna in the network with an XY mounting configuration. Originally built for the manned spaceflight program, Station 44 became part of the DSN in 1973. Located near Madrid, 3 tracking stations comprise the DSN Spanish contingent. The oldest of the Spanish stations is DSS 61, also known as Robledo 1. Its 26-meter antenna became operational in 1965. Its conjoint station, DSS 63, is Robledo 2 and has a 64-meter dish, the newest antenna in the Deep Space Network. 12 miles away is the 26-meter dish of Cebreros, DSS 62. Nearly identical with Station 61, Cebreros became operational in 1967. There are several types of deep space network facilities in the United States. At JPL, the Compatibility Test Area CTA-21 serves as an experimental proving ground for testing new DSN hardware and software. MIL-71, located at the Cape, handles pre-launch checkouts and suborbital tracking. At the Goldstone Tracking Complex, Pioneer and Echo are 26-meter antennas, while Mars is a looming 64-meter dish. Goldstone has no conjoint stations. The mammoth electronic ears of today's deep space network can and do continuously track and receive data from probes to the edge of our solar system. Receiving this precious data from spacecraft is the most fundamental purpose of the deep space network, and it means receiving signals sent with the power of a small light bulb over hundreds of millions of miles. In the spacecraft, telemetry data such as television, scientific and engineering data is converted to digital format and modulated onto a subcarrier. The subcarrier with its data is modulated onto a carrier, then amplified, typically to about 20 watts, and transmitted by the spacecraft antenna. The tracking station antenna is guided to the incoming signal by use of the spacecraft's predicted coordinates, which are fed into the station tracking subsystem. Signals from the most distant spacecraft are received by the giant 64-meter antennas. Azimuth elevation drive systems enable these dishes to point any place in the sky above the horizon. This also makes them particularly useful for assignments other than spacecraft tracking and communication. Assignments that include scanning the skies in search of extraterrestrial signals and experiments with quasars and other galactic radio sources. Although huge, each 64-meter dish is truly a precision instrument, a 6 million pound mass rotating on a thin film of oil capable of pointing accuracies within 2/100ths of 1 degree. And this is to be increased 5-fold to 4/1000ths of a degree as future probes go deeper into space and require greater antenna precision. Each antenna is parabolic to 4/100ths of an inch across its surface, and its geometry amplifies an incoming signal by a factor of 1.5 million as it reflects the signal to the focal point of the giant dish. At the focal point, a subreflector focuses the signal into a feed horn in the Cassegrainian cone in the center of the dish. From the feed horn, a few meters of waveguide ducting carry the signal to the maser amplifier located in the cone of the antenna. Liquid helium keeps the solid-state ruby maser at 4.2 degrees Kelvin. At this low temperature, the maser can amplify the signal by a substantial amount while adding only a small fraction of noise. Below the cone, mounted in the structure of the main dish, is the upper electronics room. There, the first stages of the receiver-exciter subsystem down-convert the signal to a frequency that can travel through up to several hundred meters of low-loss coaxial cable and arrive at the control room receiving equipment. In the control room, subcarrier demodulator assemblies separate the data and route it to key subsystems within the station. From the demodulated signal, the station tracking subsystem provides radiometric data such as angle pointing data, Doppler data for velocity measurements, and ranging data for measuring interplanetary distances. Although spacecraft travel at several miles per second, constant technical advancements achieved by the DSN and JPL mathematicians now enable precise velocities to be measured within 1 millimeter per second. Distance to the planets is measured accurately within 15 meters. The telemetry science and engineering data, which was coded by the spacecraft, is routed to the station telemetry subsystem. The telemetry subsystem decodes the data, records it on tape, and routes it on to the station wideband or high-speed data subsystems. These subsystems retransmit the telemetry data and radiometric data to JPL. The communications equipment linking the station with JPL is known as the Ground Communications Facility, usually referred to as GCF. The GCF uses a combination of commercial landlines, NASCOM circuits, and commercial satellites to rush data to the network data processing area. There it is processed, recorded, and sent to the Mission Control and Computing Center and the Network Operations Control Center. From these locations, the data may be sent to science or engineering teams at JPL, Ames Research Center, or other mission operation centers in the United States and abroad. Frequently, incoming radiometric data reveals the need to change spacecraft trajectory, velocity, or attitude. In such cases, Project Flight Control at JPL sends the required coded command information through the Mission Control and Computing Center and on to the command subsystem equipment at the tracking station. The command subsystem arranges the command in proper format for transmission and outputs a modulated subcarrier to the exciter in a receiver-exciter subsystem. There, the subcarrier is phase modulated onto an S-band carrier and sent to the high-power transmitter located in the antenna structure. The precision-designed antenna concentrates the high-power signal to a very narrow beam, a beam capable of reaching out to the most distant planets in our solar system. The two-way flow of data between the station and mission control is constantly monitored by the DSN monitor and control system. At the deep space stations, this monitor function is performed by a subsystem called Monitor and Control. This subsystem receives equipment performance and status information from other key subsystems and digital data handling assemblies. The Monitor and Control subsystem can also send key assembly status information to JPL. Data monitoring at JPL is performed at two main physical locations. The Network Data Processing Area monitors and displays real-time data, produces permanent data records, and sends real-time data to the Mission Control and Computing Center. There it is monitored and displayed in the Network Operations Control Area. Also at this location, operations personnel validate the data quality and distribute it to various DSN users, such as flight control, science, engineering, and navigation. Before each mission, simulated data is used to test the network and verify its capability to track the new spacecraft and acquire data. The Network Operations Control Center originates the simulated test data and sends it through the Ground Communications Facility at JPL and over GCF data lines to the Simulation Conversion Assembly at the tracking station. This assembly can be made to retransmit the data back to JPL, or it can simulate its own telemetry and radiometric data, which can be test routed within the station or transmitted to JPL for system verification and troubleshooting. The Deep Space Network exists to advance the frontiers of science and technology, and it uses an advanced concept of organization called matrix management to maximize its efforts. The essential feature of matrix management is that it provides a structure within which many different and largely independent divisions and contractor groups can work together toward common goals. NASA employs the California Institute of Technology as a contractor for many research and development programs. Caltech, in turn, maintains several non-academic R&D facilities, among them the Jet Propulsion Laboratory. JPL, which is supported by NASA, is itself responsible for several R&D programs, including those designed to explore the solar system using unmanned spacecraft. Funding and project requirements for each deep space mission pass from NASA to JPL's Office of Tracking and Data Acquisition. Here, the mission's requirements are broken down into various phases and tasks, and these are assigned to specific divisions within JPL. The Systems Division is called upon to provide navigation data type and accuracy requirements for each mission. JPL's Quality Assurance and Reliability Office is responsible for the inspection of the network's mechanical hardware and operational software. DSN communication and data processing systems are developed by the Telecommunications Science and Engineering Division, while the Applied Mechanics Division develops the DSN mechanical systems. To help accomplish their assignments, the JPL divisions may employ outside contractors. Thus, each mission benefits from the best experience, expertise, and state-of-the-art techniques available in the entire aerospace industry. Along with planning for specific missions, there's the day-to-day maintenance and operation of the deep space stations. Three separate organizational elements within the Mission Support Operations Division have responsibilities in this area. In addition, day-to-day maintenance and operation of the network's overseas stations is the responsibility of local organizations in Spain and Australia. These local organizations are funded directly by NASA, and their activities are coordinated through the Mission Support Operations Division. Personnel manning the three Spanish stations are employed by Spain's Instituto Nacional de Técnica Aeroespacial, the National Institute of Aerospace Technology, usually called INTA. The Australian stations are managed by the Australian Department of Science. Managerial personnel at the stations are directly employed by the Department of Science, while the operations personnel are under contract to that agency. As the Deep Space Network evolves through the late 70s and into the 1980s, plans call for tracking and receiving data from still more spacecraft sent on still more complex and demanding missions. Larger aperture antennas, bigger than even today's giant 64-meter dishes, will be erected to receive signals from probes going ever deeper into space. The DSN will be a major participant in the soon-coming project SETI, the Search for Extraterrestrial Intelligence. And there are plans to put a deep space tracking station into Earth orbit. As it continues to expand, the Deep Space Network will owe much of its success to the spirit of international cooperation and personal commitment that has permeated it since its inception. Certainly, the DSN has always been more than a complex of antennas, hardware, and software. It is a worldwide network of people, dedicated people, who might well admit to being intrigued and perhaps even fascinated by the exploration of space.
U-Matic.